So, alright, so our main goal today is to prove the following theorem. Which is called the Chinese remainder theorem. And it's an extremely old theorem, as the name suggests, just because China's old. Or the United States of America remainder theorem would clearly be very new by mathematician standards, but it's not. Okay, so theorem is the following. Suppose the setup is you have integers m and n that are co-prime. I'm not going to write down that they're integers. This is kind of the default. And then a and b are other integers. Okay, alright. They're integers. But they don't have to be co-prime. A and b don't have to be co-prime. Then, the system of equations, x congruent to a mod m, and x congruent to b mod n, has a solution. And it's unique modulo m times n. So I will prove it. Okay, so what I need to do is show that it has a solution. And let's say it was just one equation, x congruent to a mod m. Can anybody think of a solution to that equation? Like an integer that solves the system. Pretty easy, right? A. So A solves it. So if there were one equation, we just say, well, let's just take x to be A. Just note that x equals A solves the first one. Like that particular integer works. So here's our strategy. All we're going to do to show there's a solution is try to change this one in a way that still solves the first system, but then change it in a way so it'll also solve the second system. That's it. So what we want, this is just like an idea, what we want is to write, so our genuine solution, whatever it is, it's going to be A plus some multiple of m. So our idea is to find, or show there exists a t so that this solves the system. So find t such that x equals a plus tm solves the system. Because notice, no matter what choice you make for, let's write it really big here in case you can't see what I'm writing. No matter what choice you make for t, it's going to work in the first one. It has to continue to work in the first equation, no matter what integer t you put in there, because it works. So all we have to do is just think, okay, let's just basically look at what happens if we stick this in the second equation and see if there has to be a solution. And if there is, then we're done. We've proved it. So consider I'm just going to take the second equation, and instead of writing x, I'm going to write a plus t times m, congruent to b mod n. We can prove that this equation has a solution in t, that is, there's some integer t that satisfies it. Then we just take that value of t and plug it back in here, and certainly that x will work in the first one, because we haven't messed it up at all, and it will also have to work in the second one, because that's exactly how we made it. Questions? Good? Bad? Confusing? Ridiculously clear? Okay, good. So now, question, just forget about everything so far. Does this have a solution? Assuming that m and n are co-prime, a and b are integers, t is an integer, etc. So I just rearrange it a little bit. This is the same as t times m congruent to b minus a mod n. But notice m and n, they're co-prime. So you can multiply both sides by the multiplicative inverse of m modulo n. So in fact, this has a solution, namely t equals m inverse times b minus a. mod n, where this guy exists because the GCD of m and n is equal to 1. Or you could, we could do it exactly like in the book and just say we proved a theorem right at the beginning that whenever you have an equation, something times something co-prime to the modulus equals something else, then there's a unique solution. And so we're just using that. Okay? So there is a t that satisfies the equation, and hence you just use that over here, and boom, you definitely have a solution to this system. Let's try one by hand just to make sure we totally understand what's going on. Okay, so let's just try it. So we'll try kind of the simplest one imaginable. X is congruent to 2 mod 3. X is congruent to 3 mod 5. Okay, the hypothesis 3 and 5 are co-prime is satisfied, so we're good. A is 2, B is 3, M is 3, N is 5. Let's see what the solution is here, modulo n. Well, you have to watch out. You have to choose a t that's an integer that is congruent to this number modulo n, and then you use it over here, which is a subtle point. You can mess up that step if you're not careful. Oh well. Okay, so we consider the equation t times m. M is just 3, so t times 3 congruent to b minus a, which is 1, modulo n, which is 5. So we're nicely using everything we have. Can anybody think of a t that solves that system, or that equation? 2. 2 works. 2 times 3 is 6, which is 1 mod 5. So we could take t equal to 6. T equal to 6 works. You can choose any integer that works. So that's an integer, and it works. And now our x, you mean t equals 2. Yeah, I don't know why I read that. 6. That's so good. Okay, t equals 2 works. T equals 6 does not work. That would be 18, which is not 1 mod 5. Thank you. So x is now a plus t times m. 2 plus t, which is 2, times m, which is 3. And that's 8. And 8, you can now just go back and check. 8 is 2 mod 3, and 8 is 3 mod 5. So it works. And this will work in generality. And the only step that is hard computationally is finding this solution. And there's an algorithm to do that that involves the extended Euclidean algorithm. So the number of steps is polynomial in the number of digits of your numbers. So it's efficiently doable. Okay? Any questions? So we now have this theorem. Yes?
So to generalize to a case where we have few systems, we just take the solution mod and then.
Exactly. Yeah, exactly. So his question is, what if you had x congruent to c modulo r? And m, n, and r seem to all be pairwise co-prime. That is, they have no common factors at all whatsoever. Well, all you have to do is find a solution to x congruent to a mod m and x congruent to b mod n, and then that would be a single number mod m times n, and you could just take that and you basically collapse this into a single equation mod m times n, and then you pair that off with this one right here, and you'll get a solution to the thing mod m times n times r. So by iteratively applying the theorem, you can treat any number of equations. Okay? All right. Now I'm going to reinterpret this theorem in a more algebraic manner, which will, I think, naturally lead to understanding the Euler-Phi function better. So here's a more algebraic way of thinking about the theorem. So, let's consider Z mod, okay, Z mod mz means the integers modulo m from 0 up to m minus 1 with arithmetic mod m, and Z mod nz is the integers mod n. And it feels backwards to write it. I'm going to write it the other way because it feels uncomfortable. I'm going to write Z mod m times nz, and and then I'm going to write z mod mz cross z mod nz. By the cross, I mean the set of pairs A comma B, where A is in z mod mz and B is in z mod nz. It's the Cartesian product of two sets. And this is z mod mnz. We have a map here, which I'll just call, I don't know, F, where given an element, I don't know, x in here, it gets mapped to x modulo m and x modulo n. So that's what F does. It just takes a number and reduces it mod m and reduces it mod n. What we just proved is that that map over there is onto, or surjective, right? Given any choice of A and B, you choose anything in z mod mz, anything in z mod nz, there exists an x that maps to it, that simultaneously is one or the other. So the Chinese remainder theorem, at least the part that I stated here and proved, I didn't actually prove the unique mod mn part yet, but what we just proved is that this map is surjective. We proved this. Okay? Yes?
Do we still only know that for when M and N are
Co-prime.
prime one another?
Yep.
Okay.
In fact, let's see, it's completely false if M and N aren't co-prime. That's not surjective. For example, you could map, let's see, if you take z mod 4z, you map it to z mod 2z cross z mod 2z, what happens is you can just go through each of the elements here, but you only ever end up getting 0, 0, and 1, 1 in the image, which is not the whole image. So it's not surject on there. So it's really, so it's in fact just completely false when M and N are not co-prime. Okay, so that's surjective. By the way, how many elements are there in in z mod mn? M times n. Pretty easy. So this set has cardinality m times n. And the cardinality of z mod mz is by the same argument m, and this one's n. So in fact, this is a surjective map of finite sets. So that implies that it's a bijection. Or if you like ring theory, it's an isomorphism of rings from this one to that. This is an isomorphism of rings. But if you just like sets, it's a bijection of finite sets. And by the way, we just proved, using the fact that a surjective map between finite sets of the same cardinality is an injection, we just proved the other statement about uniqueness, kind of by accident. Okay? So now we know the uniqueness as well. And we also know that we have this map. Now what's this have to do with the Euler phi function? I kept mentioning that as motivation. So the Euler phi function is the cardinality of the numbers in here that are co-prime to mn. That's what the Euler phi function of z mod mnz is. So phi of m times n is the cardinality of z mod mnz star. These are the elements that are co-prime to m times n. Phi of m, by just kind of by definition almost, is the cardinality of z mod m z star. Phi of n is the cardinality of z mod nz star. And I hope, well, the idea is that if you put stars everywhere here, then the bijection that you got before putting the stars gives you a bijection after you put the stars there. And that gives you that this number is equal to the product of these two numbers. So, I'll just write more. We get another bijection. So there's a map from z mod mnz star. If you take an x that's co-prime to m and n and reduce it mod m and n, you get two numbers that are also co-prime to m and n. I mean, if you don't share a common factor with m times n, you definitely don't share a common factor with m, or then. So, a map like this to z mod mz star. But the same number also gives you an element of z mod nz star. And this map has to be injective and surjective for the same reasons that this one is. So this map is also one-to-one and onto. I mean, step by step, it has to be surjective because if you have an A that's coprime to M and a B that's coprime to N, we know there exists an X that's congruent to A mod M and congruent to B mod N, and then you just check it has to also be, it's automatically coprime to M and N, because it's just a simple argument. So this is surjective, and this map was one-to-one, so this map on a subset has to also be one-to-one. So if you have a map that's one-to-one, it's certainly one-to-one when you restrict it to any subset. So we have a bijection again. And that just proved that the Euler phi function has this property that phi of m times n is phi of m times phi of n. Okay? And by the way, the Euler phi function is going to play a major role in the RSA public key crypto system, which will be seen shortly. So it's important. And just to give a name to things, so a function, g, from the integers to anything where you can multiply. Well, I'll just say to a group, I guess, g, is multiplicative. Really, I'll take the positive integers for safety. Is multiplicative if when A and B are co-prime. Actually, I'll use n and m to be kind of. When n and m have GCD1, then g of n times m is g of n times g of m. So it's not a homomorphism. It's like if you know about groups and stuff, there's a notion of homomorphism where for any two elements of your group, g of a, any two elements n and m, g of nm is g of n times g of m. This is not that, because there's this additional condition that the GCD is 1. And as I hope I've made evidently clear with all these examples, like with the Euler phi function, phi of 4, it's certainly not the same thing as phi of 2 times phi of 2. Because that thing's 1 and this thing's 2. So this is a notion that comes up a lot in number theory that kind of looks like a homomorphism but isn't. So let's write not a homomorphism. Homomorphism. You have to be careful because you might think it is. Okay, so the example is the Euler phi function is multiplicative, but there are many other multiplicative functions out there of interest. What else did I want to tell you today? So that's everything that I had a very, very pressing need to tell you. And there's basically the rest of the chapter is about how to efficiently, by hand really, compute things like this inverse. And then two other things where I don't want to tell you much about doing it by hand, but you need to have a sense of why it's fast. And one of them is kind of surprising, but so you can compute a to the power of b modulo n quickly, even if a and b have, and n all have 100 digits, all of them. Even if A is a 100-digit number, and B, likewise, and n likewise. So even under that possibly scary thing, it turns out that if you try to compute this, it's extremely fast if you use the right approach. So that's the last thing I wanted to tell you about. So in the book I go through great detail to show you how to do it by hand, but definitely not going to do it by hand in here. Also, if you were to type into Sage a caret or maple or whatever, a caret b mod n, something like that, this would never finish. What would happen is it would try to write out, so if you try to write a to the power of b and then reduce it modulo n, well, if a and b both have 100 digits, a to the power of b has a huge amount of digits. If you think about it, it has, so it's roughly, so if a has 100 digits, it's a number like, it's roughly 10 to the 100. And if b has 100 digits, then it's 10 to the 100. And so the number of digits of the result is 100 times 10 to 100, which is a lot of digits. So it's 10 to 102 digits. That would take a long time to write out. Like, literally, there would be more digits than particles in the universe. Sorry. So you can do this, but you definitely don't want to do it by simply computing a to the power of b. What you do is use two tricks. One trick is that every time you do an arithmetic operation, you always reduce modulo n so that your number never gets too big. But that still isn't enough to solve this problem. How do you do this quickly? Because if you still, I mean, just looking at this the way I've written it down, you'd still have to multiply a by itself, b minus 1 times. So this is by definition a times a times a. That's a lot of a's right there. b minus 1 a's, or b is b a's, but there's b minus 1 multiplies. And that's 10 to the 100 multiplies, which again is far longer than the age of the universe, sorry. So you can't do it that way. But there's a trick. What you do is you write b in binary. And then you reduce this to just doing a couple of squarings of a. And it makes it super fast. So that's the trick. You write b in binary. So you don't multiply these all out stupidly. You keep squaring a, and every once in a while you include one of the squares. So let me kind of show you how this works. It's just a little algebraic identity, but it's extremely powerful. And it's the sort of thing that, I don't know, if you're an engineer trying to implement RSA and you didn't know about it, you might try to implement it like this and it would never work. So you can only do like toy implementations. So it's a trick. But what you do is you write a in binary. What's it mean to write a number in binary? That means you're writing your number as a sum of powers of 2. Okay? So let's write b as a sum of powers of 2. I'm just going to kind of fake it and go, it's 1 plus, I don't know, 2 squared plus 2 cubed plus 2 to the 17, something like that. Obviously, there could be a lot more powers of 2 here, but maybe, and then it's 2 to the 127. Okay? Figuring out this representation is incredibly easy. It's instantaneous. In fact, your number is already represented that way inside the computer. But you can do it by dividing by 2 repeatedly and taking remainders and recording when you get a 1 as a remainder when you do that. So that's a to the b. That's this. But now you rewrite this as a times a to the power of 2 squared times a to the power of 2 cubed times a to the power of 2 to the 17 times, I'm going to get rid of the dot 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 because I'm lazy, times a to the power of 2 to the 127. Okay? That kind of looks promising, and you'll do everything modulo n. So in order to get, say, each of these terms, just compute a and square it, and then square that, and square the result, and square the result. So that's the same as a to the power of 2 to the 4. So if you were to just take a and square it, and then square the result repeatedly 127 times-ish, then you'll get this number right here. So you can actually easily get every single one of the terms appearing here. And the amount of work you're doing at any point, it's never more than like a few hundred arithmetic operations. A few hundred arithmetic operations is massively less than 10 to the power of 100 arithmetic operations, which is what you're looking at over here. So it still looks somewhat daunting to do, say, by hand or whatever, but it's dramatically faster than you might expect that you'd be able to do this calculation. And that one thing is one of the main reasons that most public key crypto systems, especially the RSA crypto system, are actually practical, because it's ridiculously easy to compute a to the power of b mod n, where all three of these have 100 digits. Okay? We'll start next time with more discussion about this, and I think I'll describe exactly how the RSA crypto system and also the Diffie-Hellman crypto system work on Monday and Wednesday next week.